Okay, so we have been talking about function approximation. And the idea is that we have a value function, we have a policy, we want to be able to approximate the value function and policy at every point of time. And the notion of approximation is we want to approximate it in a language that the computer can understand. So we should be able to query that particular function. We should be able to query the value at a specific point. In some cases, we should be able to take the derivative of that function. And so we talked about parametric function approximators in the previous lecture. We talked about linear function approximation. We talked about neural networks. And we talked about regression trees. Okay, so the goal for today is to so those were parametric function approximators. So today we are going to talk about non-parametric function approximators. So the first one is known as local averaging. One thing that I do want to mention here is the value function. Whenever you are storing the value function, especially in the context of continuous state, continuous action problems, which is what we are studying in this particular class, you want the value functions to be differentiable because you have to optimize. You have to do the minimum of the current cost plus future value. So ideally, you want everything to be. I'm sorry. So you want everything to be differentiable in the value function space. Policies doesn't have to be differentiable because I don't care about how we are representing the policies. The only thing that is important for policy is to be able to query the value of that function at a specific at the current state. That's all is needed. We don't care if we can differentiate the policy or not differentiate the policy. That's not our main job. Okay, the value function does need to be differentiated because you want to solve a minimization problem. And of course, you can solve a minimization problem by just evaluating the value, the cost plus future value at a bunch of actions, and then you can take the minimum value of u star. That's one way to do it, but in this particular class, we have said everything has to be gradient based, right? So we're not doing non-gradient based optimization in this class, and therefore we want to be able to differentiate the value function. Okay, so what is local averaging? So I have a value, I have xi's, yi's, I equals 1 to capital N. This is my data set. Let me use D to denote the data set. So I have n points in my data set. I want to find a function h that maps x to y. I'm assuming x is an n-dimensional object and y would be a p-dimensional object. So p could be 1 in the case of value function, p could be m in the case of policy. So what does local averaging do? So what we do is we split the set x union of I equals 1 to, I'm using p here, okay, doesn't matter, xi, and xi's are disjoint. I define y I'm defining px is equal to, so for a given x, let xpx be the set containing x. I'm going to draw a picture that will make this thing clear, but I just want to write down what the local averaging does. So for a given x, I figure out what is the set in which this particular x lives, and then I'm going to define my h hat of x. Let me use a hat here. H hat of x is equal to the average of ypx, where yp equals to the set of yi such that xi is in xp. Maybe I shouldn't use I here. Let me use P goes from 1 to capital P. Yeah, I think this one works better. Okay, so what are we doing? How are we defining the function? How are we approximating the function here? So I have a bunch of data points. This is my set capital X. This is my corresponding set capital Y. I have a bunch of points here. X1, I have Y1, this is X2, this is Y2, this is X3, this is Y3. And I'm going to divide this set into 3 partitions. So this is my X1, this is my X2, this is my X3. I give you a point X. Okay, I'll let you guys write, and then we'll talk about it. Okay, now I give you a point. Let me draw a few more points. X4, X5, X6. And then I am giving you a point, let's say X here. And the question is, I want to approximate the value h of x, h hat of x. I want to figure out what h hat of x is. So this is the data set I have. So I've computed the value at each of these xi's. I've solved this optimization problem. I've computed the value. The values are stored in yi. So I have this xi, yi pairs. Now I'm asked at the inference time, I'm asked that, okay, this is my x right now. I need to figure out what the value at x looks like. What are we going to do? So this x lies in x3, okay? And x3 contains x3 and x4. I'm going to look at y3 and y4, and I'm going to average y3 and y4, so I get some point here. And this would be my h hat of x. Okay, so I'm going to average all the values of y that lies in the set where x3 and x. So I'm going to average all the values of y corresponding to the points in the set capital X3, and that will give me the value of the function at x. Does that sound reasonable? This is known as local averaging. You can create very, very fine partitions of the space, and you can get better and better approximation of the function. Is this a continuous function or a discontinuous function? Any idea? So no matter what point I pick here, they are all getting mapped to this particular point in the space. But now if I move here, I've just crossed this line slightly. Now I'm in x2, and now I have to take the average of x2 and x5. So this is y2 and y5. So this is my corresponding y for a point here, right? So I moved from here to here, and my value of y changed so significantly. So it's not a continuous function approximator. Okay, but it's a way to define a function. It's called local averaging, and this is one way by which you can approximate a function. Not a good function approximator for value function, very good function approximator for policy, especially if you have a very fine grid. This kind of function approximation, or this kind of, where do you find policies that would be, where do you think there will be a policy where you look at neighboring points, you average the value at those points, and that's a very good action to be taken at that particular point X. So generally speaking, if you have a spatiotemporal process, so something that is like, for instance, in Uber case, Uber has to match the rider to the driver at every point of time. And so in those kind of problems, the policies it implicitly has the spatiotemporal nature, where if there is a driver nearby to this particular rider, I have solved this problem, this optimization problem of how to match the rider to driver. At this point, I have to match the driver here. At this point, I have to match the driver there. Now, the person called a taxi from somewhere in the middle of the 2 points, and now I'm going to match the rider to the driver that is in that particular vicinity of the local averaging point. So in some cases, this might be a good function approximator. It's not very clear where, but you can imagine, like, as you go into the job market and as you work on different problems, you will be able to figure out where this kind of function approximator for policy would make sense. Okay. Any questions on this before I raise? Do we use any parameter here? Did we use any parameter here? Theta i's? We didn't use any theta I. So it's not that it's so just because we didn't use theta, it doesn't mean that it's non-parametric. Non-parametric has some other meaning, but in this particular case, we don't have any parameters to train. So technically speaking, oh, here is a question, trick question. Remember, we need to, for given x, we need to figure out what is the set where this x lies. Okay. Is this an efficient operation? Is it, if I give you an x and I give you arbitrary partition of the state space of x of Rn, is it easy for you to figure out what the appropriate partition xp is? Generally speaking, it's not that easy. Okay, because these partitions could be arbitrarily complicated, but there are some ways to partition which might make things easy. For instance, if you have x, if your partition xp is x such that norm of x is in p2 p plus, sorry, yeah, p2 p plus 1. This is the 2 norm. Does it make, is it easy to check for 2 norm? Right? It's easy to check if the 2 norm of a function of a point is between p and p plus 1. So how to query, how to create this partition so that you cover the entire x is also a non-trivial problem. And I'm sure as you grow in your career, you will be able to figure out what is a partition that makes sense. Another partition that makes sense, AP is less than equal to x is less than equal to BP. So now you can easily figure out by some sort of quantization or ceiling or floor function, you can figure out which partition x belongs to. Does that make sense? So this kind of stuff works beautifully when you have GPS data, when x is a GPS data, so you have longitude and latitude, and you have like the city boundaries given by AP and BP. Okay, so city is like a square in the map, then you can easily figure out where this particular person is coming from. So for instance, when Uber is aggregating, remember, Uber is a worldwide company. So people are asking for cabs from all over the world. And I can open up. So, I've traveled internationally. I can open my Uber app anywhere in the world. I can open it in Canada. I can open it in Italy. I can open it in France, and so on and so forth. And immediately, within a matter of a few milliseconds, Uber needs to figure out what is the city that I'm in and what are the drivers nearby. So they do have to do this query of which city I am in, and they do this. They probably are using something like this to figure out what's the city I'm requesting. So they look at my longitude and latitude. They have the bounding box of the city, and then they figure out, okay, this guy is calling from this particular city. Let's find a taxi cab within that city. So this query is something that you have to be worried about and you have to think about all the time, especially if you are serving millions of users per second or hundreds of thousands of users per second. Okay. The second function approximator is k nearest neighbor. So I have the data set B, xi, yi, I equals 1 to n. I divide the k nearest neighbor of x as xi such that norm of xi minus x is among the k lowest distances from x. So I look at xi minus x, I evaluate that, and then I pick the k nearest neighbors of x within that metric. And then the h hat of x is average yi such that xi is in k nearest neighbor of x. So very similar to the local averaging, except that now instead of partitioning the space, you're just looking at k nearest neighbors of the point x, and then you're taking the average of all corresponding yi's. This one also is a discontinuous approximator, but it's probably a good approximator in the inventory setting. Which is if you have X is your current inventory level and U is how much inventory you want to order, you can use something like this to approximate the policy. Okay, so all the discontinuous function approximators are very good approximators, could be a good approximator for policy. Although, if you look at companies like Google and many of the robotics companies, they tend to be using neural networks for approximating the policy as well. So they use neural networks for approximating the value, and they use neural networks to approximate the policy. But you can choose to use some of these other function approximators for approximating the policy. The third one is Narayana Watson kernel. The idea here is my h hat of x is summation k x xi yi over I equals 1 to n summation I equals 1 to n kx xi kx x prime is exponential minus these are known as kernel functions, or in general just kernel. I'm not very careful about the norms here because you can pick one norm, two norm, infinity norm. It doesn't matter what norm. I mean, it matters what norm you pick, but some norms might be better for your problem than others. Okay. Is this a continuous function approximator for these kernels? Is it continuous function of x, h hat? So let's look at each of these kernels. Each of these kernels is a continuous function of x, continuous function of x, continuous function of x. In fact, it's differentiable functions of x. So this is continuous function of x. This is continuous function of x. We have a continuous. In fact, we have a differentiable function of x if you're using one of these kernels. In fact, they are infinitely differentiable functions of x. The only parameter that is used here is the sigma that you see here. Okay, so this sigma is very useful in figuring out how quickly this kernel should decay if you go away from x prime. If your sigma is extremely large, the kernel will not decay very quickly. If your sigma is very small, then the kernel will decay extremely quickly as you move far away from x prime. So as this term x minus x prime grows, this kernel reduces its value very rapidly if sigma is very small. Now, of course, it's not obvious to you, but this kernel is actually used in transformers. Okay, so the transformer model uses neural networks to generate yi, and then uses this kernel to generate the function approximator h hat of x. And then they have multiple such layers all over the place uh, in order to create that transformer infrastructure. Okay, so in some sense, this function is currently being used in a lot of valuable companies. Okay. Any questions so far? Okay, so what's the problem statement? We have a data set D, which is xi, yi, I equals 1 from n. So yi could be the value functions evaluated at xi. Yi could be the policy evaluated at xi, so either min or argmin. Now I have to fit a function so that I can use that policy. I can store that policy on the rocket. I can store the policy on a computer. I can store the policy on a robot. So I need to store it in a computer. So I need to compute this h hat. So one way to compute the h hat is to have this local averaging approach. Another way is to use the k nearest neighbor. Another way to use is Nadaraya-Watson kernel method to store this function. This one is discontinuous, discontinuous, continuous and differentiable as long as the kernels are continuous and differentiable. Okay. Another form of non-parametric approximator is the linear interpolation. I'm sure all of you have used linear interpolation at some point of time in your life. So linear interpolation is another form of non-parametric function approximator, and you can use quadratic interpolation. You can use another form of interpolations as well, like splines. So all of them comes under the broader umbrella of non-parametric function approximators. The problem with all of those methods, interpolation methods, is that it works beautifully if you have one-dimensional or two-dimensional system, and it completely breaks down as your dimension grows higher. The current race in the market is we want to work with extremely high dimensional systems. We want to control a humanoid robot. We want to control a complicated robotic dog, or we want to control a very complicated 500 megawatt power plant and things like that. So the linear interpolation kind of sort of doesn't work in those situations, which has extremely high dimensional state space. So X is of the order of r raised to 50 or r raised to 100 or r raised to 200. One of my master student is working on a robotic snake, and state space is, I think, 300 dimensional in that problem. So X is 300 dimensional. Okay. If there are no further questions, I'll then talk about random function approximators. Any questions so far? No? The idea in random function approximators is that, if you think about many of these situations, if you have very large data set, like n is of the order of a billion, it becomes extremely difficult to evaluate some of these functions. So you have a billion xi's, you want to find the 10 nearest neighbors of a point x. How would you do that? Right? It's a complicated situation. Same thing here, you have a billion xi's. For every x, now you have 1,000 requests or 100,000 requests coming every second. For every x that comes in, I now need to evaluate 1 billion of these kernel functions and then multiply it by yi and then take this weighted average. Is that an easy task or a difficult task? So if you have to do it 1 per second, it's easy. Maybe with 1 billion parameters, maybe it's not easy even for that. But if you have to do 10,000s of them, it becomes very difficult. So if that is the situation, you tend to use random function approximators. I do want to caution here, random function approximation theory has been studied in the literature in the last 10 or 15 or so years. I don't know of any real application that is using random function approximators. So at this point of time, it's all theory. Hopefully 5-10 years later, one of you will actually put it to practice in some system that you might be working on. Okay, so there is a random basis function. H hat theta of x is summation I equals 1 to n. Oh, this n should be different. Theta I pi x. So it looks like a linear function approximator, but now these phi's are actually not handcrafted. These are completely random. So phi of x looks like cos of omega I transpose x plus bi. Or pi of x sine of xk minus ti.
Is the actual sign with a G or just?
No, this is sign with a G, like the sign +1 or -1 kind of thing. And this xk is the kth component of the function x. So this omega I is completely random. So you pick a Gaussian vector. You pick like these n number of Gaussian vectors and you construct omega I and bi using the Gaussian distribution or Gaussian random variable. And then you define your function phi I of x in this way. And then you optimize for your theta I in order to fit the function. So then it becomes a least square problem. We all have studied how to solve least square problem, right? So we can use least square problem to solve this, to be able to define this function h hat of theta. So use least square to get theta star. So we talked, by the way, we talked about parametric function approximators in the previous class, and we said how exactly to find theta star by solving an optimization problem. So you'll have to do something similar in this particular setting as well. These phi's are known as basis functions, okay? And because it's a random function, because you have generated these variables, ti is generated randomly, omega is generated randomly, bi is generated randomly, so you call it a random basis function. It's no longer a deterministic function. If you had handcrafted it, so going back to 2000, if you were a graduate student in 2000, your advisor will tell you, here is my x could be an image, x could be a video, x could be a language representation, and you would have to carefully sit down and think about, okay, how do I define an edge detector, how do I define this transform of the image, and then handcraft this feature. Today I'm telling you, you don't have to handcraft the feature, just generate these Gaussian random variables and then define the function in this way and take this n to be 1 billion. Okay, so you can define this function. You maybe in your graduate school you might define like 5 or 10 or 15 of these functions, but if you take 1 billion of these, you can generate it in an afternoon and then you can keep using it for the rest of your life. So that's the idea of random basis function. It was popularized in 2008 by some researchers, so that's when people started looking into it. Random forest. Okay, so in order to define random forest, first I have to define a random tree. So what's a random tree? So I have x, let's say this is x1, x2, x3, three-dimensional x. I'm going to define a tree, x2 greater than 5.6, yes, no, x1 less than 1.3, yes, no, x3 greater than 1, and x3 less than 5, yes, no, 3, 2, 5, 7. So at each of these places, I put a condition. I look at one of the elements of x. I come up with a completely random numbers here, 5.6, 1.3, 1, 5. Put random values here, 3, 2, 5, 7, and so on and so forth. What I have created is a random tree. Okay, it's a completely random tree. You give me an x, I'm going to go through this random tree, go through all of these leaves, and figure out what the value of that particular random tree looks like at each of this. The leaf node, the final node, will tell me what is the value of that function for that particular value of x. So that's one random tree. Now imagine you created hundreds of these random trees, and after creating hundreds of these random trees, each of these phi is a random tree, And now you use theta I in order to mix these random trees and define the function h hat of theta. Okay, so you do the same thing. Your h hat of theta of x is summation theta I tree I of x. I goes from 1 to n. So this one is one of these trees. Is this a continuous function approximator or discontinuous? Is this a continuous function of x? Yes. Is this a continuous function of x? No. So if you use this phi of x, you get a continuous and differentiable function. If you use this phi of x, you get a discontinuous function. Is this a continuous function approximator or a discontinuous function approximator? This one is discontinuous. At every node, you have a discontinuity and you get completely different values because the value comes from all the way down to the leaf node. So the random forest would look, the function would look something like this. If you look at, this is my h hat of theta of x and this is my x. A random tree would look something like this, and you're collecting a bunch of random trees, optimizing the value of theta I, and that's what gives you this random forest. And then random forest is a very powerful function approximator. This was essentially proposed back in 2000, and then a package called XGBoost came out, if I'm not mistaken, in 2015, 2016. And then it took the world by storm, because if you are training a neural network, it's going to take you 10 hours. If you're training using XGBoost, it takes you 10 seconds. And you get a function approximator in 10 seconds. It's a discontinuous function approximator, so may not be useful for all the tasks. But for simple tasks, XGBoost works beautifully. So the training is very fast. The inference is very fast because computers can store this data structure very well and they can traverse this data. So given an X, they can evaluate the final node extremely quickly. I mean, this is studied under the umbrella of data structures. I'm not a data structure person, but I'm sure there are people in CSE who study data structures. And so they have designed over the years good data structures to be able to evaluate the function very quickly. So if you look at, I don't know, because all of this information is private information of the companies, but I won't be surprised if Amazon Prime recommendations and Netflix recommendations and so on are using these random forests to figure out this is the movie that you are going to like, that you want to watch right now, and then it serves all that movies to you. Okay. So this is random forest, a very good function. I'm a big fan of random forest. It's just that because I need derivatives, I don't use it very often. But if I didn't have to use derivative, this is my go-to package for doing function approximation. Any questions on this? In the Amazon Prime example or Netflix example, what is X? What is this X? And what is this? What is this h hat of theta? What exactly is this telling you? So you have to think about what is. So you have to tell me what is X, and what is this h hat of theta of X telling me? You are close. You are close. Anybody else wants to give it a shot? What is X and what is h hat of theta? And your ratings and your reviews and things like that. So X is an extremely high dimensional vector. So in the case of Amazon, X would be, like if you're buying stuff on Amazon, X would be a 128 dimensional vector. So each of us for Amazon is 128 dimensional vector. Okay. So Amazon thinks of us as a 128 dimensional vector. We have a query. Amazon then evaluates this function and tells me that, okay, if I'm looking for a computer, this is the computer that has the highest score, this is the computer that has the second highest score, third highest score, fourth highest score. So they use that information to score, figure out what is the personalized score for me for each of the movies or for each of the items or each of the products. And then the top 10 products, top 15, top 30, top 50 products are essentially shown to us on our browser. Okay. And by the way, I know that we haven't talked about reinforcement. I'm teaching another course in reinforcement learning. We haven't talked about reinforcement learning, but when we talk about policy, this is known as a recommendation policy. Okay, so figuring this h hat theta, it's called a recommendation policy, and that actually is done using reinforcement learning. And reinforcement learning starts from the dynamic programming equation that we talked about. Okay, so the whole area of reinforcement learning and what we are studying is actually very intricately connected. In fact, I did talk about rollout algorithm in my reinforcement learning class. And I didn't talk about function approximation in my reinforcement learning class, but we did some crazy function approximation theory in that particular class. If you're interested, it's on YouTube. You can take a look at it. Bootstrap aggregation. Some people call it bagging. So what is the idea of bootstrap aggregation? You give me a data set, I can train a neural network that uses that data set and figures out what the input-output mapping of that data set looks like. So I have this h hat of theta. So I have this data set. Where did the data set go? Okay, I erase the data set. So I have this data set D, and using D, I can fit this function and I can get an h hat of theta of x, right? That's something we've been talking about for quite a while. The bootstrap aggregation has the following philosophy. So the philosophy is I can use the entire data set to create a very powerful function, or I can divide the data set into smaller data sets. I can create a weak function for each of those data sets, and then I'm going to aggregate all of those weak functions together in a new function. And that gives me this bootstrap aggregation. So this is union of I equals 1 to n di. So I constructed these n different data sets from the original data set. I can use IID sampling from the original data set in order to create this new data set. And then for each di, I create a model h hat theta I of x. And then I define my h hat theta of x as summation wi h hat theta I of x. I equals 1 to n. And then I can optimize my w's in order to make sure that my true function reflects the true values of w. So w's are optimized using least square. From data set to h hat theta, you can use any parametric or non-parametric. Function approximator to get h hat theta. This strategy was used recently in DeepSeek's large language models. They had a lot of weak learners, and then they aggregated all the weak learners. So the weak learners are these smaller transformers, and then they aggregated all the smaller transformers in order to get the large transformer, and that's their DeepSeek model. Okay. So I told you 3 parametric function approximators, 3 non-parametric function approximators, and 3 random function approximators. So remember that because I am coming up with this data set in a random fashion from D, each of this function approximator is completely different from other function approximators. And then I'm averaging them. So because these are all random functions, as a result of the random data sets that you have generated, it's a random function approximator, not a deterministic function approximator. Okay. So I've completed the entire discussion on how to do value function approximation and how to do policy approximation when you're solving a dynamic programming problem. So the key idea in that setting is you generate xi's randomly from the space. So if you're sending a rocket from here to the moon, along the trajectory you generate random xi's. Then you compute the value functions around those at those values of xi's, and then you use any of these function approximating classes in order to store that value function and in order to store the policy at each of those at each time. So each pi t pi t and each vi vt would look something like one of these h hat of theta uh, that we have talked about so far. And the dynamic programming in general is very useful wherever there is a dynamics involved. So whether it's ride sharing, whether it's sending a rocket to the moon, or whether it's catching a rocket back into the base station. So all of that uses some form of dynamic programming. And in all those situations, some form of function approximation is needed in order to be able to store the value function in the policy. Some of the things that you have to worry about, and that's not part of any curriculum within the university, but that's something that will be asked in your interviews, is the system design questions as to how do you store, how do you train these policies using data, some of which we talked about, and then how do you store and infer these policies in a very large scale system at the Google level or at the Facebook level or at the Uber level. So those are the things that you will have to prepare for when you are going up for interviews or internships at many of these companies. So that pretty much sums up the entire course. Now we are done with the entire syllabus of the course. And so far, nobody has sent me an email about what topic is it that they want to study further. So I am not sure what I'm supposed to teach on Monday and next week. And I'm not sure what I'm supposed to teach after Thanksgiving. So if any of you have a request, please feel free to reach out to me so that I can teach something on Monday. And if not, then I'll cancel the class on Monday onwards, all the way until the end of the semester. And the quiz 3 is out, it's available. It's on the dynamic programming. So we are done with the entire dynamic programming. So I've published the quiz. You can go back and take that quiz. Midterm 2 is already graded. So I've distributed midterm 2. But if you haven't picked up, please come to me after the class. And the project is due, I think, maybe 8th of December or something like that. So if you have questions on your project, feel free to reach out to me. My office hours will still be on my calendar. So if you have any questions, feel free to drop by in my office hours. And any other questions? There's no final exam. So we are done. Okay. So good luck with your future endeavors. And if you have any questions, feel free to reach out. Yes.
Do we have any other homeworks?
No, no other homework. Six homeworks, 3 quizzes, 2 midterms. I think that was plenty, and a project. So that's a lot of evaluation. So hopefully